I thought it was time to put some math with the theory. So in your packet, if you look, you should be able to find a worksheet titled Fluid and Fluid Dynamics Problems. And what we're going to do today is to do our best to work through those. I did take the liberty of drawing out some diagrams ahead of time. If you get caught behind, just push pause. I'm going to try to do this in one take because editing is a pain in the neck. So we'll see how it goes. You ready? There's already a typo in the first problem. I hope this is the only one. It says, the flower vases that we used in class have a length of 19 centimeters. They were perfect cylinders with very straight sides to them, a radius of 2.25 centimeters, and a mass of 225 grams. The vase is set into a pool of alcohol that has a density of not 7.9, but 790 kilograms per meter cubed. Let's go with that. 790 kilograms per meter cubed. How far from the top of the vase will it reach equilibrium? What's that height going to be? Oh, wait, what's the magic word? Did you hear it? Equilibrium. So the sum of the forces is going to be equal to what? That's right, 0. So we're going to have the buoyant force up minus the weight down. So the buoyant force is going to be equal to the weight. Now, if you go back to what we had learned already about fluids, the buoyant force is the density of the fluid times gravity times the volume of fluid displaced equals the mass of the object. Really, it's the weight of the fluid is equal to the weight of the object. Boom, boom. Now, where do we go? Well, I see right away that G's cancel. And it's asking for height. That's going to be wrapped up in this volume of fluid that is displaced. So I'm going to go ahead and solve it up for VF. I get the volume of the fluid displaced. It's going to be the mass of the object divided by the density of the fluid. And let's try to get all of these units to match up. So for mass of the object, I'm going to go with 0.225 kilograms and divide that by 790 kilograms per meter cubed. And I'm going to get some number that's pretty small. It's a vase. It's not going to have meters cubed of volume, right? Meters cubed is pretty big. So 0.225 divided by 790, and I get 2.85-ish times 10 to the minus 4 meters cubed. Now the question is actually asking, I'm going to take this. The question is actually asking how far from the top of the vase. So I know that volume is equal to the area times the height of the fluid. There we go. Area times the height of the fluid. That would be the height of the fluid displaced. So if I just do volume divided by area of the area equals the height of the fluid. So 2.85 times 10 to the minus 4 divided by pi and the radius here. The radius is going to be 0.0225 squared. Yeah, because you got to convert it into meters. So second function answer divided by, don't forget to put parentheses around that pi. I got the height of the fluid is going to be 0.179 meters. Now, if that is true, then that means this value right here, the amount that's under the water, is 0.179. And since the total height is 0.190 meters, that height above the surface, I don't know what you want to call it. How about H? We'll just call it Is that 0.19 minus 0.179 or 0.011 meters? Whew. Now, the particulars of that problem, they don't matter. But what does matter is that the sum of the forces equals 0. The reason that vase doesn't sink is because gravity is acting down, but there's a buoyant force back up. After that, you just figure it out. Number 2, water is pushed through a horizontal pipe with a diameter. Diameter? What the heck? Whoever made this was just a jerk. Oh, that was a diameter of 4 inches, flowing with a discharge rate of 0.0050 meters cubed. It flows into a smaller pipe, reducing the diameter to 1.5 inches. What's the velocity in the smaller tube? So discharge rate. Now the units for that are meters cubed per second. So that to me is clearly the change in volume divided by the change in time. Okay, now change in volume is going to be the area times the displacement divided by time. Oh, that's right. We've already done this. The change in volume, or the volume flow rate, is going to be the area times the velocity. So if we take this newly earned formula and plug it in. Now, I've got an answer of 0.005. 0.0050 meters cubed per second equals the area, which is going to be pi times 1.5 times 0.0254 squared. Now, I already see it. I see it. Relax. That parentheses was in the wrong spot. How do you feel about that? Take a second. Thank goodness you guys are AP Physics 2 students and you get math. If you back up a little bit, I got volume per second equals the area times the little v, the velocity. I plug it all in. Or, better yet, I go to the end of the page where there's an answer key, and I got 4.38 meters per second. If somebody could double check that for me. Adam, actually Sam, I believe you've already got the answer. Did you get 4.38 meters per second? Yeah? Nice hustle, Sam. Thanks. Good. What was the point of that problem? I don't know. I think it was so that we could learn the word discharge rate. Discharge rate. And deal with units. All right. Number three. Number 3 actually is a really neat problem. Here we go. A water tank with a radius of 1 meter stands such that the base of the tank is 10 meters in the air. A small hole occurs at a height of 3 meters below the top surface of the water. How far from the base of the tank in the X direction would you need to place a barrel in order to catch the water? We are going to ignore the height of the barrel. All right, you know what this is. This is a beautiful XY motion problem. But in order to find Vx, we have to use Torricelli's result. Torricelli's result says that when you have an open container with an open spout at the bottom, the velocity is just going to be equal to 2g delta h. This is the velocity, sometimes called the velocity of efflux. So I'm going to go ahead and plug in the values that I know and get that velocity. So 6 times 9.8, take the square root. Did you guys get 8.74? Good, because the answer is really 7.69. ish meters per second. And that's going to come out. We are going to assume that that wall is perpendicular or straight up and down, so that when it's coming out, it's going to come out in the x direction. So what's my next step? My next step is to make my XY chart, just like the old days. Doesn't that feel good? So I know that the velocity in the x direction is going to be 7.69 meters per second. I know that the acceleration is 0 in the x direction because there's nothing speeding it up or slowing it down. Distance in the x direction, oh, that's what I'm trying to find, and the time. So let's look in the y direction. The initial velocity in the y direction is going to be 0. It's going flat. Bob Crowley would appreciate that. The final velocity, I don't know. Displacement, oh man, what am I missing from my diagram? Charlotte, what am I missing? That's right, my positive arrows. That's embarrassing. I'm going to make right and down positive this time. So my displacement is going to be plus 10 meters. And the acceleration is going to be plus 9.8 meters per second squared. I can solve for the time that it takes for that water to reach the ground. Now, is there air resistance? Of course there is. We're not going to worry about this. This is high school physics. We're good. Actually, it's college physics. Sorry, that stinks for you guys. But we can solve for the time. D equals V naught T plus 1/2 AT squared. At this point, gosh, if I knew how to edit better, it would just fly right through. You guys should be doing this on your own. Come on, you've been practicing all year not listening to me. Why are you starting now? So 2 times 10 over 9.8. Take the square root. Time equals 20. 20 divided by 9.8. 1.43. That water is going to be in the air for 1.43 seconds. Man, 10 meters is pretty far. 30 meters. That's a far jump. So to wrap it up, the distance in the x direction is going to be the velocity in the x direction times time. So I'm going to have 7.69 times 1.43. So the distance in the x direction is going to be 10.9. Let's call that 11.0 meters. All right. The application of Bernoulli's there was actually pretty easy. We got to do an XY motion problem. All right, we're back. We're on page 2 of the fluid and fluid dynamics problems. And let's jump right in. Here we have an airplane wing. It has a total wing area of 75 meters squared. It has a mass of roughly 4,500 kilograms. If the speed of the air below the wings is 200 meters per second, all right, what velocity over the top of the wings is necessary in order to keep the plane at a constant altitude? Constant altitude. Okay, so what two forces are acting on that plane's wing? Well, in the y direction, which is what we're worried about right here, we're going to have two forces. We're going to have mg down, and we're going to have a force of lift up. Now, what causes that force in the lift? A difference in the pressure. We talked about that in the other video the other day. Now, I can say the sum of the forces is going to be equal to 0. So in the y direction, that is. So I'm going to have the force of the lift minus mg equals 0. Oh, so the force of the lift is just going to be equal and opposite the weight. Back up. Of course it is. Otherwise, the plane falls. All right. Now, the force of the lift, that's something we should get into. So pressure is going to be force divided by area. So a difference in pressure is what causes the force to lift. So the force of the lift is going to be delta P times A. So delta P times A equals mg. Do I know what delta P is, though? What am I looking for? I'm looking for the velocity over the wing. I think I've got to do this. I'm going to go with Bernoulli's because right now this feels like a dead end. I don't know if it is. So let's see. So if I write Bernoulli's out, I've got P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. If your head's not spinning, you're not paying attention. Push pause, catch up. And once you do, here we go. The change in height is going to be the same. This wing might have a height of 1 meter, but it's traveling through air where the density of the air doesn't really change from one spot to the other. And the difference in potential is going to be so small. I'm going to let those two just cancel out. Now, if I solve it up and get a difference in pressure, so if I say P1 minus P2 equals 1/2 rho V1 squared, V2 squared minus 1/2 rho V1 squared, I get a difference in pressure equal to 1/2 rho V2 squared minus V1 squared. All right. Now, P1 and P2. P1 is going to end up being greater. Down at the bottom, P1 is greater than P2. So this is going to be V1, and V2 is going to be the speed at the top of the wing. Now over here, I already said that the difference in pressure is going to be mg divided by A. So why don't I plug that in? Oh, now we're getting somewhere. I wasn't so sure we were going to get anywhere there. Now, I'm looking for V2. All right, let's go another step. Let's do it. You guys can do it. So I got 2mg divided by rho of the fluid times the area equals V2 squared minus V1 squared. Did I know that's what the formula is? You guys know darn well that I did not. I didn't. I can't remember that. Some of you can, but I can't. So there it is. But we came to it using conservation of energy, which Bernoulli's equation, and pressure equals force divided by area. So let's keep going. 2mg divided by rho times A minus V1 squared equals V2 squared. Now at this point, you should push pause and plug it all in, because I'm going to push pause. This thing never pauses. All right, I'm back. Whew. So I'm not sure if I made the sign error before or after I left you and pushed pause, but right there, that should be a positive sign because I added that V1 squared to both sides, and I ended up with a final answer of 203 meters per second. If you look at that, that means that the change in wind speed above and below that wing is really minimal. Yeah, interesting. All right, number 5. Whew, boy, that was a long problem. Number 5. If a solid lead cube with sides of 2 meters is placed into water, what is the buoyant force or force of buoyancy on the cube? Will it float? No. What about if it's placed in a large pool of mercury that has a density that's given? All right, so I already took the liberty of drawing these pictures. I'm sure you guys can do that right now. But if I were to draw, if you need to push pause, go ahead. If I were to draw in the forces, in water, we're going to have mg down and the buoyant force up. Notice that I clearly drew the buoyant force as much smaller than the weight, because you're not going to get a lead cube to float. So the buoyant force is the density of the fluid times the gravity times the volume of fluid displaced. The buoyant force in water is going to be the density of water times 9.8 times its volume, which it says it's 2 meters on a side. Gosh, that thing's huge. Okay. So the buoyant force is going to be equal to 1,000 times 9.8 times 8, or 78,400 newtons. And that's still not nearly enough to lift this thing up, because it's a 2 meter cubed lead cube. Next, what if it's sitting in a large pool of mercury? Well, we can see that the density of mercury is greater than the density of the lead. So if I look at that, it will float. So what does that mean about our forces? Well, it means that the sum of our forces will be equal to 0. So we're going to have the buoyant force acting up minus the weight of the lead down. So those two are equal. I should probably go and draw in my forces. Buoyant force down. And lost my focus for just a minute. I get in car accidents. Mg down, buoyant force up. Okay. Now, the buoyant force is going to be the density of the fluid times gravity times the volume of fluid displaced times the mass of the lead. Now, I could find the mass of the lead, but I can do something even easier. I know that the mass of the lead is going to be the density of the lead. I know it's not L, but I don't want to write PV. Density of the lead times the volume of the lead times gravity. This right here, that's the mass. Now watch what happens. G's cancel out. And I'm looking for, will it float? Oh, wait a minute. This question didn't even ask. If I were to keep going, I could find that the volume of fluid displaced is going to be a ratio of their densities times the volume of the object. I guess I could have just stopped right there. And number 6. What's the total pressure on a diver under 12 meters of water? Oh, we're back to buoyancy. I like these. Pressure equals density of the fluid times gravity times the height or depth below. And it's 12 meters below, so that's pretty easy. So the pressure of the fluid is the density. It's in water, so 1,000 times 9.8 times 12, the pressure caused by that fluid. I got 1.18 times 10 to the 5th. Pascals. Why is that not the right answer? How come? Amanda, I know you see it. I know you do. Abel? I know you don't. No, I bet you do see it, Abel. I'm just kidding. Nice. Because what, Abel? You're right. Good call. Amanda, I know you knew it too. Right here, we have the atmosphere also acting on the fluid. And the key is that the question asked about the total pressure. So the total pressure, sometimes called the absolute pressure, would be the pressure of the fluid plus the pressure of the atmosphere. All right, so I got my 1.18 times 10 to the 5th, and it's been a little while, but the pressure of the atmosphere is roughly 1 times 10 to the 5th. So the pressure total is going to be about 2.18 times 10 to the 5th pascals. Nice job. Nice job. Next. Number 7. The Venturi tube has an opening with a radius of 0.1 meters. Water enters the tube with a velocity of 5 meters per second, and by measuring the difference in pressure, The velocity of the water in the narrow part of the tube is 8 meters per second. What is the diameter of the throat? The throat. Oh, this is the throat, where it gets constricted. It's like where a boa constrictor would, like, that's where they suffocate you around you. Yeah. So how do I solve that? Well, I know that the volume in has got to be equal to the volume out. And if I wanted to discuss it in terms of flow rate, if I divided both sides by delta T, now I have flow rate. Volume, flow rate, discharge rate, whatever you want to call it. Then I recognize A1 V1 equals A2 V2. And that's little v, as in velocity. So I'm trying to find the diameter of this. So I'm going to keep going with what I got. So area 1 V1 over V2 equals area 2. I plug in what I know. Pi times 0.1 squared times the velocity of 5 meters per second divided by the velocity it's leaving with, which is 8 meters per second, gives me A2. You know what? I'm embarrassed. That should really be pi R2 squared. So let's take the square root of both sides. That's going to give me, I could have taken that 0.1 out. 0.1 squared times 5. Oh, I can feel you guys drifting. So am I. Almost done though. I got 0.079. 0.079, yeah, ish meters. Multiply that by 2 to get the diameter. And I got 0.158 meters. I hope that's the right answer. Green highlighted with green. That's what I got. Number 8. Do it on your own. I'm tired. You're tired of listening to me. You totally got this. Thank you guys. We made it to another lesson. Somehow it's just a lot easier when you're in class and not on the video. I don't know how you guys are watching